Hello, I'm Keita Takenouchi from NTT Data. In this video, I'll introduce our work on the synthesis of SQL queries from example tables. This video consists of three parts. First, I'll describe the overview of our tool PATSQL. Then, I'll explain the algorithms used in PATSQL. Finally, I'll show you the experimental results. Let's start with background. Programming by example is a technique that synthesizes programs from examples. In this case, input and output pairs such as 3 and 7, 2 and 5 are given. Then a function 2 times x plus 1 is automatically synthesized. This example is very trivial, but there are practical PBE tools in some domains, such as string manipulation or regular expression. In this work, we propose a PBE tool called PATSQL, which synthesizes SQL queries from example tables. For instance, if a user specifies input and output tables like this, then an SQL query is synthesized. So non-expert users can obtain SQL queries just by giving input and output tables. Let me show you a demonstration on how PATSQL works. In this screen, there are two tables. The upper one is output table, and the other one is input table. When I update the table, a query is automatically synthesized and shown in this area. Now, there are 3 columns in the output tables. 3 columns are projected in this query. Now, let's try to synthesize more advanced query. Each record in the input table has ID, price, and date. And there are 3 distinct IDs here. So let's try to extract latest price for each ID. For ID 001, the latest price is 130. For ID 002, 580 is the latest price. For ID 003, 230 is the latest price. Now, a complex query is shown here. This query has a nested query and the max operation inside it. PATSQL can synthesize such complex queries in less than 1 second. Why is PATSQL so efficient? Let's see the algorithm next. In PATSQL, programs are synthesized in our DSL. Before describing how PATSQL works, I'll explain the definition of our DSL. Our DSL is based on relational algebra. Each operator takes more than 1 input tables and produces a new table. For example, project operation projects some of the columns in a table, while select operator filters out records according to the given condition. We have 8 operators in total. Here is an example program in our DSL. This program is represented as a syntax tree, and the evaluation is performed in a bottom-up manner. For example, when this is the input table, the result of select operator is like this, and the final table is produced by projection. PATSQL performs sketch-based program synthesis as in prior work. In this framework, programs are represented as sketches. Sketch is a program whose arguments are abstracted as squares, and Sketch is used to determine program structures. First, sketch enumeration is performed. This is an exhaustive search to find program structures that satisfy the examples. Then, sketch completion is performed for each sketch. Specifically, this phase fills the squares in a sketch with concrete structures. Now, this is the target sketch, and these are input and output tables. When we replace the square in the select operator with a concrete predicate, C3 equal T, we can obtain an intermediate table. Next, we want to fill the square in the project operator. But before we fill the square with the concrete projected columns, we can infer the output table always have 2 rows because the project operation does not change row count. Producing 2 rows is inconsistent with the fact that output table has a single row. Thus, this filling is invalid, and we don't need to search projected columns anymore. This kind of pruning is a major advantage of a sketch-based synthesis. But there are issues in prior work. A serious issue is that filling projected columns causes combinatorial explosion. For example, when the input table has 3 columns, filling projected columns needs these patterns. The number of patterns grows significantly as the input column size increases. Thus, prior work can only support a small number of columns and is not so useful in practice. In contrast, PATSQL can support a large number of columns. How does PATSQL resolve this issue? Our key insight is lifting projection operator. Some transformation rules are known in relational algebra. This rule means project and select operators can be swapped. We can easily infer projected columns in the second sketch by comparing output and intermediate tables. In this case, C4 in the output table corresponding to C2 and C5 correspond to C1. So the projected column should be C2 and C1. Actually, the projection operator can always be fixed near the top of a sketch. This means we can always fill the projected column efficiently. In addition, PATSQL performs pruning based on whether projection may be possible or not. In this case, there is a column corresponding to C4, but there is no columns corresponding to C5. As a result, we can prune this sketch without filling any squares. To realize this pruning, we have introduced a new form of a constraint and its propagation rules. Please refer to our paper for the details. Finally, I'll show experimental results briefly. This graph shows the execution time taken to solve benchmarks. According to the results, PATSQL solved more benchmarks more quickly and found 89% of the solutions within a second. Other experiments also shows the efficiency of PATSQL. Please refer to our paper for the details. That's it. Thank you for watching this video.